All right, so today's video is going to be kind of a two-part deal. So today we're going to lay out some of the basics of it. You better take notes on this. There will be an assignment on your second non-Zoom day this week regarding this information. This is not hard. This is not hard, but you have to take notes to make this happen, okay? That's just how there is to it. Now, we are going to talk about a simplified version of this. In reality, there's a little bit more to it. And if you were building race engines or something, it would matter a lot about that. And just in general, if you were building engines, period, you'd look into that a little bit more too. But for our general, normal, everyday engine stuff that we do, if you understand the basics of this, you will be more than far enough ahead. What we're going to be talking about is what's called compression ratio. Okay. Suffice to say, it's this. This is the volume of cylinder. We're just going to say of cylinder when piston is at the bottom of the stroke versus volume of the cylinder. Oops, I gotta spell stupid. When the piston is at the top of the stroke. Okay. That seems really straightforward, Mr. Groom. Are you literally saying it's as simple as something like this, Mr. Groom? 49 divided by, well, let's just do an easy one I can do in my head. Like 50 divided by, like 50, Mr. Groom, when it's at the bottom, and like 5 when it's at the top. So that comes out to be a 10 to 1 or 10 to 1 compression ratio. That's literally as hard as it gets. That's it. That's it, friend. Could it come out to be a decimal? It literally could come out to be a decimal. Like for instance, if this came out to be 52.5, and when you divided it out, you got 10.5. That's right, 10.5 to 1. That's right. Well, it's not very hard. No, it's not. So what's so hard about it? Well, it's a little trickier than all of that. So here's the game. So clearly, we know how to find the volume of the cylinder. We literally did that earlier. We said the volume was equal to pi times the bore scorer divided by 4 times the stroke, right? Talked about this. And that was for one cylinder. That's all we're going to do it for, is for one cylinder this time. Remember last time we multiplied it by the number of cylinders to get displacement? That's not what we're looking for this time. This time we want just for one cylinder. And you're like, well, that's it? That's all. Not so fast, Haas. Now, here's the problem, okay? The head sits over the top of this. The head will have a certain amount of dish in it. Let me show you. Mr. Groom, just make one up. Just find us one, Mr. Groom. So 350. Ooh, heads. Oh yes. Oh yes, Mr. Groom. Yes, let's look at those heads. So if you look at the bottom of one of these heads, if I can find one, boom. What do you notice there, friends? I feel like if you come in there and look around, you see there's a little dish right there. Do you see that? Those pistons sit in a little bit of a dish. Well, that's volume. It is volume. If you were here in class, what would you make us do, Mr. Green? I would have you take clay and jam it into this thing until it would fill this bowl completely up. And then I would have you fold that clay into a cube that would be like, but let's just pretend for the sake of argument, it'd be like, I don't know, 1 millimeter by, or 1 centimeter by 1 centimeter by, well, let's say inches. Let's do it. 1 inch by 1 inch by 1 inch. It's like 1 cubic inch, Mr. Groom. That's right. Well, that volume is always going to be there because the piston will never go into that. That's right. Oh, well, that's easy. That's right. Now, again, I am going to kind of dumb this down a little bit because there's a couple other things we have to take into consideration when you're building engines. The gasket thickness, that will also determine the fact that there will always be a little bit of a spot where the piston won't go. Also, sometimes the piston doesn't go all the way to the top of the cylinder. For instance, the piston might actually stop a little bit below the top. You're like, well, so in other words, this bit right here will give you this amount of volume down here, but it doesn't account for this bit on the top. That's right. That's right. And so I think we're just going to kind of skip over that right now. Okay, I think, because I don't want to get too crazy. If we were in class, I could actually teach that a little better. It's really hard to visualize not in class. Okay? And then one more thing that has to be taken into consideration is that some pistons have what are called dish pistons. And so some pistons have the divots on the top of them, as you can see here. They are dished. Well, what does that do? Well, it gives you more volume when the piston's at the top. And so this is a flat top. The engine that I showed you that I'm building for my Bronco has flat tops, and they have barely a little bit of valve reliefs in them, but basically they're just flat. Some of these have bigger dishes. Some of them are dome, but they have a big dish on one side. And the whole point of that is to manipulate the compression ratio. That's it. If you get a compression ratio that's too high, you cannot run your car on regular gasoline. Okay? And so we're going to talk more about fuels coming up. But suffice to say that if you bought a car back in the 70s, it was frequently that it had somewhere around 7.5 to 1 compression. Back in the 70s, they were really concerned about, that was when they were first trying to come up with ways to fight air pollution. And one of their first ideas was, well, you know, if we had less compression in the cylinders, the temperatures inside the cylinders would be a little bit less. And if they did, they would not put out the same kind of bad chemicals. They put out different kinds of bad chemicals, but it wouldn't be as bad. And that was their first idea. The problem with that is when you run too low of compression ratio, you'll have really low power. So the 70s is known as a time when, you know, muscle cars were not muscular. they were bad. And other engines were just kind of, They were not made for power. They were made to just be okay and to meet certain emissions requirements that they had to meet. Likewise, on the other end of things, if you get much north of 10 to 1, okay, this is about as low as they go. Again, this was kind of back in the 70s. You haven't seen that really since the 70s. And this is about as high as they go from the factory. Okay? You've often seen, Mr. Groom, why do people buy 93 octane gasoline? Well, we're going to talk more about that. But if you had 10 to 1 compression ratio, you're going to want to be buying 93 octane gasoline. Okay? It's going to be very important that you buy super gasoline. Okay? And we'll talk more about that. You go out to the racetrack, you'll see guys out there with 11, 12 to 1, things in that neighborhood on their cars, and they have to run race gasoline. Okay, we'll talk again a little bit more about why that is in the coming days. But they're running a lot higher compression in their vehicles to try to make a lot more power, and it does. Problem again is, of course, you will run into issues with, again, pollution. That was a big deal. Now, we have other ways of dealing with pollution nowadays. And so we've been able to increase the compression to get more power again, get the engine running better, doing better things. We're attacking and we're cleaning up emissions from a different standpoint now. Okay, again, that was what you had to do back in the day. Now, again, this is pretty much factory cars fall in the middle of this somewhere. So like where, Mr. Groom? Right around 8.5 to 9? Yeah, about 8.5 to 9-ish in general for gasoline cars is a pretty common-ish, again, ballpark. Well, I only buy fancy sports cars like Camaros and like the Mustang, the 350 GT Mustang came out a couple years ago and stuff. I only buy stuff like that. Okay, well then you're going to be closer to 10 to 1. Yeah, I mean, that's just it. Okay? But if you're just driving normal grocery getter car, 8 to 9.5, and 8.5 to 9, maybe you see 9.3 or something or whatever, but it's in that ballpark. Okay, that is just always going to be true. Okay, for your average car. Okay, from the factory again. Okay, now diesels, they will be in the high teens to low 20s. To 1. That was where your diesels will lie. Okay, And we'll talk more about why that is in the coming days. So we're going to spend some time talking about fuels, how they burn, you know, how do we light the fuels in diesel versus a gasoline engine and that sort of thing. But they need compression ratios that are higher. Again, typically in the high teens to low 20s. Okay, especially in the old days, you saw a lot of them were in the low 20s. And they've come down in the last few years. They just do things differently. When I say the last few years, last 15, 20 years. Now that we've been doing a lot of electronic injection engines, they've been able to decrease that and do it differently. And so it's just a different way of doing it. Again, same exact calculation that we're going to be talking about here. Okay? So in general, it's going to go like this. Compression ratio, boom, boom, is going to be equal to, always, you have pi times the radius, or times the bore rather, squared, divided by 4 times the stroke, plus the volume of the cylinder head, plus the volume of the piston. I'm going to put piston dish. Okay? Now, again, I'm going to leave off the part about the fact that on some engines, the piston doesn't quite make it to the top of the cylinder. And on some engines, well, on every engine, in theory, you should take into account how thick the head gasket is. That said, for the sake of what we're talking about right now, I'm not going to worry about that. Okay? Now, this volume of the piston dish, okay, I think I'm going to leave it on there. If I don't tell you otherwise, just pretend it's a flat top piston, okay? If I don't tell you otherwise, we'll assume that it is a flat topped piston. Okay? Now, what do I mean by that? So then on the bottom, then what are you going to divide by? You're going to divide by the volume of cylinder head. And that, by the way, that's volume of cylinder head has a name. It's called the combustion chamber. Okay. Plus the volume of the piston dish. So the only thing that goes away is this part? That's right. That's right. Now, which of these are the biggest numbers? This thing by far is the biggest of these three numbers on top. It is the biggest. So in essence, you're got this huge number plus a little bit plus a little bit. And then you're going to divide by a teensy tiny amount. And so you're going to end up with somewhere in the neighborhood of, it's going to be, the top's going to be somewhere in the neighborhood of, let's say, 9 times bigger than the denominator. Mr. Graham, I got a 27,000 to 1. No, you screwed up, pal. You screwed up. I got a 1 to 2, Mr. Graham, then you really screwed up. I'm telling you right now, they have to be in the 8 to 9.5-ish, 8.5 to 9.5-ish range. If it's not, you screwed up. Now, I will say this, Mr. Graham. Mr. Graham, what if we're talking about like a 75 Cadillac? Okay, did it come out to be like 7.7 to 1 or something? Oh, okay, then that's possible, yeah, because it was in the 70s, okay? Aside from then, nah, it's going to be 8 or 9, somewhere in that neighborhood, okay? Just be aware of that. Now, let's try one, shall we? Mm-hmm. So, if we're talking about a Chevy 350, let's just say, I'm going to write that down. And I'm going to write that down only because of the standpoint of I just want to start with one that we were comfortable with. Let's have some fun. Now, Mr. Grimm, is it a V8? It is a V8. Is it a pushrod engine? You know, it is a pushrod engine. Good for you. What's the bore, Mr. Grimm? Glad you asked. Hey, the bore is, come on, dummy. The bore is 4 inches. Nice. Hey, what's the stroke, Mr. Grimm? Turns out that the stroke is 3.48 inches. How do you know that? I don't know. You just memorize stuff. Okay? What if it was a 351 Windsor, Mr. Grimm? Then it'd be 3.5 inches. But whatever. Let's get back to this. Now, let's just, for the sake of argument, begin our compression ratio measurements. So it'd be pi times 4 square over 4 times 3.48. Nice. Plus, now let's go and let's just say Mr. Groom told you we want to use a flat top piston. I can do that. So that means I'm just going to add 0 on the end. You with me? Because there's no dish in this piston. It's just flat. Which, by the way, Mr. Groom, thank you for helping us do that. You're welcome. Because I'm cool like that. Now, I am going to come back in here. And let's go pick out a a head for this thing, okay, shall we? Now, Mr. Green, how would you really pick it out? I'd pick it out because it's the coolest looking one. I'd pick it out because it's the cheapest one. No, I would not. I would pick out the one that I wanted that would make the appropriate amount of power for my engine that, yes, would not break the bank. Okay, you literally can always find more expensive ones. Are you with me? You can always find quote-unquote better ones. Always, 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 always. Okay, now, right here, for instance, this one here, it says 64 cc's. What does that mean? Well, let me clue you in, friends. I'll take you to the website there. Now, it says a 64 cc chamber. What do you mean, Mr. Groom? I mean that when you have your head here, like so, nice, there's this divot right here where the valves lay in. It's a beautiful divot. If you were to fashion clay into this divot and then fold it into a ball like so, or a cube like so, it would be 4 centimeters by 4 centimeters by 4 centimeters, which is 64 cubic centimeters, or if you prefer, 64 cc's. Well, Mr. Groom, why do they do it in cc's? Because I think it makes more sense than talking about it in terms of inches cubed. Yeah, now, I am not feeling the need to do this by hand. I don't need to flex, as the kids say these days. I don't need to flex with my math, yo, yo, yo. I am going to simply take 64, or 60, did I say 64 cc's, 2 cubic inches. Oh, that's hot. Look at that, 3.9 cubic inches. 64 cc sounds better because it's bigger, Mr. Groom. That's right. But I'm going to type in 3.9. Why? I'm going to type in 3.9 because, again, all this measurements over here are in inches. So I need to have inches, inches, and inches. But why do they do it that way? I don't know. I just work here. No one told me. Okay? So I'm going to break out my calculator. So 3.14. Again, please use 3.14. Now, that's 16 divided by 4 is 4. So I'm just going to go times 4 right there. Times 3.48 plus 3.9 is 47.6 on top. 47.6 over 3.9. Now, I will say this, Mr. Groom, we were buying stuff out of the Summit Racing catalog, Mr. Groom. That's right. Wait a minute. We just got a 12.2 to 1 compression ratio. That's right. Well, you said that's too big. Racing. For a racing engine, would that be possible? Yeah. Yes, it would. Well, how would I know the difference? Well, you won't. I'll tell you which one to look up, actually, in fact. So what I will be doing is I will tell you the compression or the combustion chamber. But just for a good time, let's go on Napa's website and let's see if we can just find a plain old head, okay, for just a stock engine, okay? Now, the reason I say that is because I want you to understand that, you know, if you're just buying one for your truck to, oh, for the love of Pete in a bucket, you piece of crap. Apparently, I killed Chrome. Anywho, as I was starting to say before I was rudely interrupted there, is that the idea that if you're normal, just run to the, oh, you worthless piece of crap. As I was saying, if you're just buying a vehicle or an engine, you just have an engine in your vehicle just to like run to the dump, why, a fella doesn't need to have, 8 million horsepower. Am I right? So, again, we talked about that with cams as well. So you come in here into the Napa website, I guess. Here we go. Let's just look one up here real quick. And so what I want to show you is that sometimes when you're looking at these guys, that if a person just went looking on Summit Racing, you're like, that may or may not be the engine, the head that you actually want for your vehicle. You may make it so that your truck goes super fast on the way to the dump, but it's kind of useless for pulling. Okay. And so a guy needs to know, well, what do I want this for? Am I doing this so that I can, pull and haul and do whatever? Or am I doing this so I can, win drag races or something? I mean, that's ludicrous. So, yeah. Come on, Betsy, let's go. I clicked on cylinder head. Give me the cylinder heads. Come on. Shimo. Shimo now. On the assignment that I'm going to give you tomorrow, again, not today, tomorrow, not tomorrow, but later in the week, there I will tell you exactly what size combustion chambers we're using and so forth. Right. This is a compressed natural gas head. That's cute. But notice that this one here is just a head that apparently is not. Apparently, it's a head that is not necessarily for stock combustion chamber. Yeah, anyway, apparently it's not like for racing or whatever, but they assume that you're just sticking that on your vehicle and replacing the stock one, so it's not as big a deal. There you go. So yes, there you go. So I don't know. That was for a slightly different version there. Yeah, so in other words, here you go. So down in here, and it talks about, hey, look, so different ones like, oh yeah, I was buying it from this car or that car, or whatever. Well, again, if you were buying, check it out right here. Specifically, this guy was talking about. I saw one of them was a so 76cc head. So if we came back to 76 cc's, let's actually check that out real quick. What is 76 cc's? 2 inches cubed. So 4.64, let's call it. So if you come back into here, if that's true, so that would be 4.64 instead. All of a sudden now I'm dividing by quite a bit larger of a number, and the top didn't get that much bigger. So let's see what actually happens here. So if you come back up here and grab this fella, get rid of that and put 4.64 there. And if you divide that by 4.64, what you will find is that we end up with about a 10-to-1 compression ratio. Now, in reality, it's going to be a little less than that, and that's because the stock Pistons probably are not flat top. They probably have a little bit of a dish in them. That's also probably because there will be a situation where, again, we have to, in real life, take into account the thickness of the head gasket and a few other little odds and ends. But for right now, all we're going to talk about is this situation here. Okay, it's pretty straightforward. We just say we would write this as it would be a 10.4 to 1. Okay, that's how you'd write it. Now, again, I want people to understand the basics of it. Okay, once you understand the basics of it, the rest of it's just little add-ons. Okay, what I don't want is because a lot of our class barely does any of the work. Then they're like, well, I don't even understand what you're talking about at all. Oh my God, it's so hard. Great. So, yeah, that's what I want. So I'm gonna pause you for a jiffy, and then we'll come back and do this next one again. All right, so a little 2.3 liter Ford back in the day, a 4-cylinder car, whatever. Had a bore of 9.604 centimeters. By the way, that's 96 millimeters in case you're playing along at home. 7.94 centimeter stroke, or 79.4 centimeters or millimeter stroke if you prefer. And it had a 68 cc combustion chamber. So the compression ratio is simply going to be the following. Equals, pi. By the way, a minute ago I screwed up on this calculation. I was doing this ahead of time before I didn't waste your time. And I was doing it and I forgot to divide by 4. Well, what happened, Mr. Grimm? What happened? What happened? I'll tell you what happened, friend. What happened was I ended up with something like 2,299 somehow. And I'm like, what the heck? Why am I getting 2,299? And I'm like, that is the actual displacement of the engine, but I didn't times by 4. The problem is I didn't times by 4 is I forgot to divide by 4 first. So in essence, it was as if I had times by 4. And I'm like, oh, yeah, that's a problem. Because when I divided, guess what I got? Mr. Groom got like 30-to-1 compression. Guess what? Diesels won't even run that high of compression. Okay? So that's a problem. So pay attention to what you're doing. Make sure you don't screw it up. Make sure if you mess up that you catch it. Notice that the top is now going to be 643. Whoa, that's weird. And 68's on the bottom. Like, literally, I don't know what that is, Mr. Room, but I feel like if it was 680, then it would be 10 times bigger than the bottom. That's right. It's not 10 times bigger. It's like 9 some odd times bigger. It's 9.45 times bigger. So what we say is this is a 9.45 to 1 compression ratio. Okay. Now again, for those of you who have had some experience with vehicles and whatever, or you're more interested in this, we can talk more about that, you and me, and talk about some of the aspects of the vehicle that you'd want to deal with there. It's funny. I was listening to a bunch of old NASCAR racers that got together in the late '90s, I think it was, and they videotaped it. Yeah, back in the day, you didn't like just put it on your phone. Okay, it was like videotaped. Anyway, and so they were all sitting around talking about how they cheated and stuff, and that was kind of that's what you do in NASCAR. It was kind of cool. Back in the day, some of the people who checked your cars, they would get lazy and they'd always check the engine that was on the driver's side, closest one or whatever, and that's the one they'd always check. So some of the mechanics realized that, well, I can make the whole rest of the engine a lot bigger, because they had back in the old days, 427 cubic inch limit to the engine size, and but then later on, now it's down to 358 cubic inches. It has been for a long time. Okay. Now, interestingly enough, apparently they told this story about how one time that the guy who normally checks engines wasn't there that day, and so somebody else did it, and he pulled a different spark plug out. And what they ended up doing, you made sure that piston was clear at the bottom on that cylinder, and they just filled it full of water. And it should take a certain amount of water. Well, it took a lot more water than that. Well, he built that engine so that the piston that was in the number one, the one that they always checked, was taller, and so when it went down, it didn't go. It had where it basically they changed that cylinder right there. That they made that cylinder smaller than all the rest of the cylinders, and apparently it probably sounded kind of crappy running, but it didn't run that great. But at high RPMs, it probably didn't make as much difference. But what was interesting about it is that they ended up catching the guy, and so the engine was a lot bigger than it was supposed to be. And so when you run the race, you got disqualified and stuff. It was kind of funny. Okay. Can't remember which car that driver that was, but it made me laugh a lot. Now, here is another one. I am going to pause this once again. Okay, I'm back. So here's an engine. It's fairly common nowadays. By the way, remember this is an over square engine that has the board bigger than the stroke. So for our compression ratio, we're going to be doing this: 3.7 or pi, 3.14 rather, times 3.78 squared, divided by 4 times 3.622. Now, be careful. A lot of people will do this. Those people are wrong. This is disturbing. Remember, this is in, and not because you put 2 5s, because you're a dinghead and you aren't paying attention. Remember, these are in inches up here. Okay, these is in centimeters. Okay, that can't live. So what I did is I went ahead and converted for us. It's 3.7. Now this is a fairly stock situation, so it should be somewhere in the neighborhood of 10-ish, no more than 10-ish. So something's a little, something would be weird if I was much bigger than, say, 10, but it should be probably 9 something. But it'd probably be really weird if it was like, say, 12 or something. That'd be strange. So wonder what would happen. Let's just see here. Now, again, I promise you on the assignment and on the test, I will make it so that it comes out a reasonable figure. Except that Mr. Groom can't even type because he's an idiot. He's too busy yabbering his hair off. There you go, stupid. There you go. That's more better. Now, if I divide that by 3.7, I get this. I get like almost 12 to 1. You're like, that can't be, Mr. Groom, because they just drive down the street. I concur, sir, ma'am. So let's go look it up, shall we? So what I'm going to do is I'm going to look up 5.3 Pistons, 5.3 Chevy Pistons, and I want you to see what they typically look like when you get a stock set of pistons. So if you look in here, look at that piston. What do you see? Mr. Kim, I see a dish in that piston. I do too. So what does that say to me? Well, it says to me that when it's clear at the top, that dish is going to contain some volume. And in fact, what's really going to happen, and so just so you know, what's really going to happen is we're going to add something like, I don't know, I'm making this up here, like 1.5, maybe. What would that do to us? I don't know. Let's find out. Again, that's a ballpark, but let's just see what happens here. Plus 1.5. That's good. Nice. Divided by, parentheses, 3.7 plus 1.5. Oh, 8.8 to 1. Friends, that is a lot more like it. Okay? But again, I will make sure that on the assignments and so forth, I keep it pretty much as straight as I can. I don't want to fool people. I'm not trying to make this hard or weird or anything, but the stock Pistons have that little bit of a dish on them. Does that matter? You better believe it matters, friends. You better believe it does. Here's a flat-topped one. Guess what that's going to be? Well, a flat-topped one is going to give us a higher compression ratio because there's nothing there. But if you got one of these really big dished ones, then you're going to have an even lower compression ratio. Okay. Now, by the way, notice that says 14.5 cc's right there. See that? 14.5 cc's. Okay. Well, I can do the math on that, I suppose. 14.5 cc's. Cc's to cubic inches. Well, so it's about 0.8. So, in fact, over here, I guess I should have done this. Clear. Here, let's call that 0.9 instead. Okay, oops, 0.9. Now, if I divide by, the bottom is now going to be 4.6. You'll see you get 9.8. But again, that is a measurement that a person can actually run that would actually take normal gasoline. Okay, so again, going to bring that up. I will make sure that the ones I give you will come out nicely. I will make sure that I come up with ones that work that way. Okay. I will just mention this briefly, that in here, there's a piece that goes around here like this. There's some thickness to that. It's a gasket, we call it. We'll talk more about that later on. It actually makes this cylinder a little taller, and the pistons don't actually go all the way to the top. Okay, and so there will be a little extra there as well. So again, I will try to make it so that it's obvious for us. If we were in class, you could get your hands on some physical stuff. It would make it easier, and I would spend a lot more time on it. For what we're doing now in this situation, we're just going to pretend that this is good enough, and we're just going to roll with it because nothing else I can do about it, friends. Those of you that take Auto 2 and 3-4, if we ever run into that again, we will spend a lot of time talking about that. How would we pick the appropriate piston or what have you? Mr. Graham, if I use this piston, I'm going to get like a 12-to-1 compression ratio. Okay, well, what do you want to do with it? I just want to drive it every day. Well, that's not okay because you need race fuel for that. So no one wants to do that. But Mr. Graham, I want to go race my car at the track. Well, then that's probably about right for you. Okay, but your daily driver, Mr. Graham, is going to be like 8.5 to 1, 9 to 1. Sure, okay, 9.5 to 1. Sure, that's fine. Yeah, no problem. Yeah, you can pull that off. But you go over 10, you're going to need some really good fuel. In other words, to keep from knocking. And we'll talk more about that later on. Let's do a little Toyota. Sure. Toyota. Sure. A Toyota 3-liter. Yeah. All right. I'm going to pause you while I go get the information for us. All right. So this is one of Toyota's many 3-liter stuff that came out. This is one from the 90s. I think this was some of the ones that in the Toyota in their pickups, but this might have been one of the ones that was in their vans. I don't remember. I just went and looked. It's no big deal. I don't really care. Whatevs. It's no big deal, Mr. Cream. So the compression ratio would be equal to, again, pi times the Boer, not boring, but just the Boer squared, and then divide that answer by 4 when you're done, times it by the stroke, whatevs. And then we had a 60 cc combustion chamber. Nice, that's hot. It's like, Mr. Cream, I feel like it's not very hard to do this problem. It's not. By the way, can you see that's less than 600? If it was equal to 600, friends, it would be a 10-to-1 compression ratio. Are you with me? And if you're good with math, you realize that 9 times 60 is 540. So it would be a little bigger than 9 to 1. Shut up. It's 9.2 to 1. That's right. 9.21 to 1. Boom. There's your compression ratio for this engine. Okay? And it's not too far off. I think the actual one was 9.8 or something. So I was guessing at the combustion chamber size. I couldn't find the exact combustion chamber size anywhere for this engine. Not that it matters. It's not that big a deal. Okay. So again, I want you to jot this down somewhere. Okay. It's gonna be pi. It's gonna be the combustion. This is the volume of the cylinder. The volume of the cylinder head, which is the combustion chamber. Volume of the piston dish, if it has one, divided by the volume of the cylinder head or the combustion chamber, plus this guy. Okay. And again, in real life, in real actual thing, you'd also compute if the piston sits inside, doesn't come all the way to the top, you'd include a little bit there, and you'd also include for the intake or for the head gasket thickness. We're not going to mess with that right now, so I want you to make some notes on this, and we'll be ready to go for our second day this week.